All right, guys. So in the last video, we talked about the Schrodinger equation, which can be used to basically solve any multi-electron system. So you can know roughly with some probability where electrons are, a probability distribution map for all the electrons in any atom, right? And that's going to be really important because as we saw earlier in the course, right, electrons dictate all of chemical reactivity, essentially, okay? And so it's a super complicated mathematical expression. Computers are actually used to solve this, and thousands of researchers, chemists, computational chemists, they're called, across the world, are developing new ways to solve this equation faster and better. Okay, because it's really important, and it's so complicated. Another reason why computers are really important. If we could get better computers, we could solve this more accurately, faster. We could solve a lot of problems ranging from, coming up with a vaccine for coronavirus a lot faster than we are now to, all sorts of things, energy conversion processes, renewable energy, name any technological problem, knowing quantum chemistry could help you, okay? But anyway, if you solve this equation, what you will get out is you will get wave functions. Those give you orbitals, right? We mentioned the shapes of those wave functions give you orbitals. And those orbitals can be described by a set of what we call quantum numbers. They're quantum numbers because they come from Schrodinger equation based in quantum mechanics, okay? And there's 4 different quantum numbers. These are solutions, mathematical solutions, of the Schrodinger equation, okay? And these you do need to know because they tell you something about the shape and the size and the properties of orbitals, which is a lot of what this chapter actually boils down to, okay? So there's 4 of them. We use 4 different sets of letters to describe them. The first is N. It's called the principal quantum number. QN stands for quantum number. The second is L. That's called the angular momentum quantum number. M sub L, that's called the magnetic quantum number. And M sub S has to do with electron spin, okay? So we're gonna talk about those 4 in this video. These quantum numbers give you the properties of the orbitals. Orbitals you can think of as like zip codes for the electrons, okay? And remember, electrons are the source of reactivity in all atoms, okay? And so orbitals are going to be described by their energy level, how much energy they have, and their shape. And so a name for an orbital, one type of orbital, is called the 1s orbital, okay? It looks like a sphere here. And S, it actually doesn't stand for sphere, but all s orbitals are spheres, okay? It stands for something else. It has to do with spectroscopy, and we don't have to worry about it, but serendipitously, you can think of S as standing for sphere, even though that's not where the letter S came from, okay? I know, it's just unfortunate historical stuff that gives things weird letters, okay? And you'll see the other ones are kind of weird letters that don't really make sense, okay? But they come from historical reasons of how they were discovered through spectroscopy. But anyway, S orbitals are like spheres. So this letter tells you the shape, tells you something about the shape. And the number, the 1, tells you something about the energy. So this tells you that the principal energy, the principal quantum number is 1. It's at energy level 1, okay? It's quantized, so you're not gonna have 1.5. You're either gonna have 1, 2, 3, etc. So yeah, N is the principal quantum number. It can be 1, 2, 3, 4, etc. It can go up to infinity. But for where the periodic table is right now, it only goes up to 7, okay? Maybe someday in the future, it'll go up to 8. Right now, it only goes up to 7, and it's related to the size and energy of the orbital. On the periodic table, this is actually the rows of the periodic table. And this is the beautiful thing that we're about to do, is we're gonna connect quantum mechanics to the shape of the periodic table, and it's all hopefully gonna make sense to you guys, okay? And we can actually explain why things are the way they are in terms of chemistry, okay? But just right now, I'm telling you, the principal quantum number, solutions to the Schrodinger equation, that value N, is exactly the same as what row you are, what row number you are on the periodic table, okay? That's related to the size and the energy of the orbital. L, the next one, that's the angular momentum quantum number. That's related to the shape. that has integer values that can vary from 0 to n minus 1. Sometimes this is called the subshell, okay? So if I give you a quantum number n equals 1, I tell you, hey, I solved the Schrodinger equation, I have an orbital, and n equals 1, L can vary from 0 to n minus 1. Well, n was 1, I told you that, and 1 minus 1 is 0, so L can go from 0 to 0. L can only be 0. That's the only thing. That's what's shown here. If n equals 1, L can only be 0. All right, let's do n equals 2. N equals 2. 0 to n minus 1. Well, n equals 2. So it can go from 0 to 1. Only integers. So if you have an n equals 2, you can have an L equal to 0 or an L equal to 1. Okay? And so forth. For n equals 3, n equals 4, L can be 0, 1, 2, 3. It can go up to n minus 1, which for n equals 4 is 3. Okay? The letters, I mentioned S. S corresponds to that second quantum number, the angular momentum quantum number. Saying S, you have an S orbital, that's the same thing as saying I have a quantum number L equal to 0. Saying p orbital, that's the same thing as saying I have a quantum number L equals 1. Saying d orbital is the same thing as having a quantum number L equals 2. Saying f orbital is the same thing as having quantum number 3. And it turns out that's all we have to worry about is up to L equals 3. And so again, S, P, D, F, it looks kind of random, and it comes from historical reasons why they're given these letters. Okay, so it's not going to make sense to us right now. So sorry about that, but that's, you know, the way that science works. The L quantum number is shape, like I alluded to. So S, P, D, or F, L equals 0 is going to be a sphere type thing. Okay, so you can have a 1s, it looks like this. It doesn't have any nodes. A node is a place where the wave function, this is a mathematical function, goes to 0. So there's 0 probability at a node that an electron will be there. That's what a node is. There's 0 probability that an electron will be there. We know that 100%, the function goes to 0. The math tells us that, okay? So if you have a 2s orbital, it looks like this. You'll have one color I'm showing it as. That could be like a positive sign in your function. And then another color could be like a negative sign or vice versa. It doesn't really matter. But in between these two spheres, you're going to have a node, because if you went from negative to positive, you're going to have a 0 point. Okay, so you're going to have a node. So the 2s has one node, and it's a radial node. It's a spherical shaped node. The 3s, right, has two nodes. It went from positive to positive, or negative to positive to negative. Either way, it's fine. Still going to have two nodes, two spherical type nodes. But all these looks like spheres because they're all S's, okay? They're all L equals 0. Now, you go to L equals 1. The L equal 1 are called p orbitals. And I think of these as dumbbells or dumbbells, but I think of it dumbbells to try to remember the P. Okay, the P's look like dumbbells. They look like this. And they have a node that goes through the axis. This is sort of a more planar node, okay? Again, positive, negative, or negative, positive. You went to 0. There's no electron density at the node. L equals 2. That's another shape. It's a cloverleaf shape, okay? And it looks like this. They have two nodes. I put a question mark here, but they have two nodes. I was going to ask you in class, but they have two nodes, okay? Both planar nodes. All right. Now, if you went to a, so this would be, we'll get into this later, but this would be a 2p orbital. If you went to a 3p orbital, that would have one planar node and one radial node. We'll get into that later. But basically, as you increase the principal quantum number, N, not L, you'll start introducing radial nodes. One thing just to mention on this slide, each orbital can accommodate 2 electrons. I'll show you why in a second. L equals 2. Those are called d orbitals. Those are shaped like this. There's a cloverleaf, a cloverleaf, a cloverleaf, a cloverleaf. They have certain names: YZ, XZ, XY, X squared minus Y squared. Z squared looks a little different, a lot different depending on your definition of different. Why do they look this way? You have to solve the math. I can only, at this level that we're at, I can only just tell you the answer. And the answer to the Schrodinger equation tells you this, okay? You can solve it, but to know the answer more deeply, you need to solve the Schrodinger equation, which would take, years more of schooling at this point for all of us, all right? The magnetic quantum number. M sub L, that's the third quantum number. This has integer values between L and minus L. This describes the orientation, roughly, of the orbital in space. So if you have an n equals 1, and I told you it's L equals 0, that's all you can have for n equals 1, that's an s orbital. M sub L can go from L to negative L. Well, L is 0, so it can range from 0 to negative 0. So it only can be 0. M sub L can only be 0. You only can have one orientation for a sphere. That makes sense. Check out what happens when you go to p orbitals. When you go to p orbitals, let's say n equals 2, that's going to allow you to have a p orbital, the dumbbells, right? Or the dumbbells, as I like to call them, for remembering that they're p orbitals. M sub L can go from negative L to positive L. So L was 1, so it can be negative 1, 0, or 1. Three different orientations. An X orientation, a Y orientation, a Z orientation of the three p orbitals. Okay? What are the quantum numbers that describe the 3D orbital? Let's go through this. So 3D, that 3 tells us, that 3, let me just go right now to a pen, okay? That 3 tells us n. So n is equal to 3, okay? L equals 0. Well, S, if we made a chart here of kind of your nomenclature, letter nomenclature for the quantum numbers for the orbitals. Remember, S is basically 0, okay? P is 1, D is 2, and then there's F, which is 3. Okay? So this was a 3D, so n equals 3, and L is going to be equal to 2. That tells me that M sub L can be equal to any integers from negative L to positive L. So L can be equal to negative 2, negative 1, 0, positive 1, or positive 2. There's 5 different orientations. Why are there 5 different orientations? Those were the 5 different orientations I showed you of the d orbitals, okay? Now it's not XYZ, they're more complicated than that, and that's why you get these weird shapes. It has to do with, crazy math stuff, but that's why you have 5 shapes, okay? L equals 3 is your F orbitals. Those will have negative 3, negative 2, negative 1, 0, 1, 2, and 3 for M sub L. 7 different orientations, 7 different shapes, 7 different orientations rather. Okay. And last thing I want to just tell you on this video, right, is we've been talking about energy transitioning between states. What is it actually transitioning between? It's transitioning between the different orbitals. It's not the Bohr model. It's not orbits, it's orbitals. All right, so we made it through a good chunk of quantum mechanics in this video, and now we're gonna get increasingly connect things to the periodic table in the next video, which is exciting, I think.